Okay, we are at 1:15. We have a very packed agenda, so I might get going. We've got about 40 people, so I think we have quorum. So good afternoon, everyone. Thank you for joining us. This is the External Synergies session. We have a very exciting, action-packed agenda for you today. If I can scroll through. Okay, so we'll just start with the usual friendly reminders. There is a code of conduct for this workshop. You all signed it when you joined the workshop, when you registered. The code of conduct is applied to this session, so let's have a nice, respectful and enjoyable session. A few other reminders. Talks at this workshop are recorded, including this one. Recording has started. The videos will be posted the next working day. Emily has a little bit of work to do to extract them and post them. We will take questions on Slack, so please give thumbs up to questions you like on Slack. Please show your appreciation. Please ask questions on Slack, as you've done for all the other sessions so far. So just a few notes about the session format and logistics. The co-chairs are myself, Julie McEnery, who is the project scientist for the Reuben mission, and Rachel Street, who is the chair of the TBS Science Collaboration. The External Synergies Slack channel has been set up. I'm sure many of you have joined it already. Colin Slater, the Deputy DM Subsystem Scientist, has kindly agreed to help us monitor Slack for questions. So as those questions come in, he will queue them up so that they can be asked during the session. If you would like to ask a question during a presentation or at the end of the presentation, please raise your hand in Zoom and the chairs will queue up those questions. Just a note that we will not monitor the Zoom chat. Please ask all your questions in Slack and try to keep discussions in Slack to threads so that we can keep the discussions nicely separated into their respective topics. Rachel Street has kindly agreed to be the scribe for this session. We have set up a shared Google Doc. I've posted the link in the External Synergies Slack channel. Anyone is welcome to add their comments and thoughts and points into this shared Google Doc. A burden shared is a burden halved. So today's session, after a brief welcome from me, we will hear first from Julie McEnery, who will talk to us about Reuben synergies. I will then give you a short update on the status of the Rubin-Euclid Derived Data Products Working Group. We will then hear from Matt Hilton, who will talk to us about radio synergies. Matthew Graham will then talk to us about synergies between ZTF and ls.st. And then we'll finish with just an open question and answer session. And just to note that some of you sent us advanced questions through the form that we sent out. Thank you for this. It was very helpful to us in deciding how to structure this session and what topics to schedule. We have provided answers at the end of this slide deck to those questions, but we can also discuss them during the question and answer session. So just before we get started, I want to I just have two slides to share. One is that I want to define what we mean by external synergies. One of the things I think Rachel and I learned by looking at the questions that came in advance was that there seemed to be a lot of different understanding about what an external synergy is. And so when we talk about external synergies, what we're talking about is two things. One is the combined analysis at the pixel level of data from multiple surveys to produce cross-survey data products that augment or improve the science harvest of all the surveys that contributed data to the processing. And the other is the coordination of survey observations to maximize the overlap between surveys or to synchronize observations over specific fields. And for example, deep drilling fields, coordinating observations across deep drilling fields is a topic that's been discussed quite widely already. This is what we mean when we talk about external synergies. Things like alerts and follow-up of detections in one survey, say for example at other wavelengths such as radio or X-rays or with other messengers, or the combination of final catalog data products from independent surveys, or using information from one survey, say astrometry from Gaia, together with information from the Reuben final data products to do science or just to do science basically, is considered within the community realm. And this is not really what we're talking about when we talk about external synergies. What we're focused on is the first 2 points here, combining an analysis and coordinating survey observations so that we can produce better final data products using all the information available across various surveys to do this, to enhance the science. So we've recently just set up on the ls.st, the Reuben Observatory ls.st Community Forum, a external synergies category. We didn't have this previously, but discussion is starting to is starting to ramp up. People are getting very interested in this topic. So if you would like to participate in discussion, ask questions, post information around external synergies, please do use this category on the community forum. Okay, and now we will move to Julie, who will talk to us about Reuben synergies. I will stop sharing.
Leanne. Let me see, where is the share button?
Share button. It should be at the bottom. It's in green.
Oh, the bright green one. It will share the whole screen if I click share screen. No, it won't.
So if you click the screen.
Yeah.
Nice.
Great. So I'm going to talk about Reuben, and it is related to Reuben synergies, but I'm actually not going to talk about the synergies directly. What I would like to focus on in this presentation is a brief overview of Reuben to give you a sense of what might be possible, tips and hints on how to get more information about Reuben, and then I wanted to spend some time discussing opportunities to engage with Reuben that are relevant for people who want to work on synergies between Reuben and Reuben, and these range from getting involved in defining the Reuben surveys to some funding opportunities that would be open for people who are interested in exploring the possibilities with both observatories. So I'll start with the Reuben mission objectives. Not that the mission objectives are important for the content of this talk, but they're very important for the observatory that we're building. So if you read our top level requirements document, the order of the mission objectives are as I've listed them here. The first objective is a wide field infrared survey that will open up a very broad and interesting range of science. This is followed by more specific requirements that relate to studying the expansion history of the universe using multiple methods, exploring the growth of structure in the universe using multiple methods, conducting an exoplanet census via microlensing observations towards the galactic bulge. At least 25% of our prime mission is devoted to a general astrophysics program, which is a set of surveys on wherever. And then finally, we have a chronograph technology demonstration. And the reason to mention all of these is that our mission objectives define the observatory that we've built, the capabilities that we have, and the allocation of large chunks of our observing time. So it's helpful to understand these. But of course, a mission that will meet the cosmology and exoplanet demographics requirements that I've just described in the previous page will do a broad and rich range of other science. And I hope that when we're thinking about synergies between Reuben and Reuben, we take a very inclusive view of this. I think that we're going to find that there are synergies and enhancements that we can make working together across a very broad and rich science area. So this is the observatory, and let me keep moving quite quickly. It's got a main science instrument, which is operates from the visible to the near infrared. It's got a field of view of 0.4 by 0.8 degrees, which is small compared to Reuben, but it's big for a space-based instrument of this quality. We have 80 in 4K by 4K detectors, so we have pixel scale of 0.11. We have a second technology demonstration instrument, the coronagraph instrument, that will operate in the visible and will provide the first space-based active wavefront control for coronography. We're approved for launch no later than July 2027, and internally we're planning for or working towards a launch date in October 2026. So this is after a rebaseline to adjust for COVID impacts. So you'll possibly hear both of those dates. Somebody working on the project will probably mention the 26th date. This is the last that I'm going to show of detailed performance. If you're interested in knowing what filters we have, simple exposure time calculators, what kind of magnitudes and so on we can reach, I recommend you follow the second of the two links at the bottom of this page, and it will open, I was going to say a Pandora's box, but something more positive than that, that will let you know, give you the tools that you need to get started with Roman. I wanted to also emphasize briefly that often Roman is described as Hubble with a large field of view, but in fact, we're more than that. We're designed as a survey mission, so we perform very efficient observations. And what that means is the relative speed with which we could conduct, say, a survey of Andromeda is not faster by a factor of 200, it's faster by a factor of over 1,000. So we really do have a significant boost in what we can do. A second point to make is that the design control of systematics and precise understanding of calibration is fundamental to what we're doing. So we will have a very well understood and stable point spread function, an excellent flux calibration, and this I think feeds in to how we might use Roman and Reuben together. I thought what was particularly relevant here was to spend some time discussing how we're going to make observations with Roman. To meet our top-level science requirements in cosmology and exoplanet demographics, we have planned for 3 core community surveys that will occupy a significant fraction of the prime mission to conduct very, surveys of unprecedented scale. These 3 are the high latitude wide area survey that will provide the data needed for weak lensing and a galaxy redshift survey, a high latitude time domain survey that will provide the data needed for supernova cosmology, and a galactic bulge time domain survey that will provide the data needed for exoplanet microlensing observations. Something I really want to emphasize, though, is these surveys do need to provide the data to meet those level 1 science requirements, but what we want to do is to define the details of the implementation of each of these surveys through an open community process where the goal is maximizing the overall science return. So all of the other rich astrophysics that we expect to get from those surveys will be an integral part of how the surveys themselves are implemented. And I very much hope that the Reuben community joins in this because there's a very good chance that the science return from these surveys will be enhanced by careful consideration of how we might use those data next to Reuben. We're going to have several calls for general astrophysics survey closer to and after launch, and we do not have proprietary period for any Roman data. So all Roman science data will be fully publicly available as soon as it's processed. All that said, while I've said that we haven't defined that the implementation of the surveys will happen closer to launch, of course, we have to put together straw man surveys to verify that we really can do this science. So what I'm showing here is what we call the design reference mission. These are sample surveys to demonstrate that we can meet our science requirements, conduct all the observations we need within the 5-year prime mission. But it also gives you a sense of what the Roman surveys are likely to be. And if we have to quickly summarize where Roman sits relative to Reuben, is that we have a deep, relatively small or smaller footprint with a good angular resolution with a well understood point spread function. And just to describe quickly, just tell you what you're seeing here in red is the high latitude wide area survey. This little pink dot here is the galactic bulge time domain survey, and these blue are one example of a high latitude time domain survey. We are aware that while there is an advantage to waiting until we get closer to launch to define our observations, there is an opportunity cost with waiting. We have realized that there may be observations that would substantially benefit from multi-year preparatory activities. It would allow precursor observations, it would allow simulations, it would allow other detailed studies. So what we're considering is to select one survey using up to 1 month of observation time to be executed within the first 2 years of the mission. So this will allow for a substantive survey, but it doesn't commit to a large amount of time early in the mission. It leaves most of the general astrophysics survey time to be assigned closer to launch. So what we're hoping for from the community is for people to engage and help make the case that yes, it is useful to define one of our observations now, and if so, what is the science area or survey concept to focus on? So, for example, if we get submissions that make a compelling case that a deep field would be useful, then we would follow this up with a community process next year to define the detailed observing strategy for that deep field. We're expecting to release the request for information for this white paper process sometime in the next couple of weeks. So this is an imminent opportunity, and we would be delighted to hear from people from this community. Reuben has a set of science investigation teams. I list in the top the topics. This group comprise around 300 scientists in total. The science team contracts expire later this year, so we are entering a period of change and opportunity. We're restructuring our science community. This will allow us to adjust how we do things to be more appropriate for this phase of the mission. And it also will give us an opportunity to adjust our priorities if there's a change in emphasis from the upcoming decadal survey. So what this means is that if you have always wanted to be directly involved in Reuben, this is your opportunity. So what we are planning is 3 opportunities in the upcoming Roses Call with a deadline in early 2022. And the one I think you should focus on is the wide field instrument preparatory science, which will allow for a range of investigations of different sizes and durations to work on science preparation activities of all kinds. So this could include precursor observations, simulations, software and algorithm development. I mean, anything that prepares for and will enhance the science return from Reuben. So if you're a scientist at a US-based institution, this would provide a funding opportunity for this. We will be forming a different structure for our science teams, but the details of that will likely become more clear when we know who the teams are themselves. So to summarize, all Reuben observing time is available through open processes. The major surveys will be defined using a community-driven process that will start in a couple of years' time. There is a short-term opportunity happening right now that we'd really love you to get engaged on. Later in the year, there will be proposal opportunities to get funding. And that's all I have.
Thank you, Julie. That's really interesting to know. I'm very excited about hearing more about these opportunities and seeing them when they come up. Colin, do we have any questions for Julie?
No questions on Reuben so far, but there was one clarification from David Buckley about whether prompt follow-up of ls.st alerts is considered an external synergy, which I think is a Leanne question.
Yeah, no, I'd say no, that prompt follow-up of ls.st alerts is not considered an external synergy. What we're thinking about with external synergies is how do we make the data products that we produce better so that you could better enable that prompt follow-up by, for example, changing the areas of the sky we observe at which time, or doing a joint processing at the pixel level. I hope that answers the question. And can people see my shared screen?
Yep, we see the presentation. Okay,
so I'll move on now. And David, if you want, we can come back and discuss this in more detail, I think, during the question and answer session. I'm a little conscious that we have quite a packed agenda. Okay, so I'm just going to give you a quick update now on the status of the Rubin-Euclid Derived Data Products Working Group. So late last year, sort of early this year, the Euclid Consortium Board, together with the Reuben Observatory Director, set up a working group that was charged with designing a concrete set of derived data products that could be shared promptly and simultaneously with both the Reuben and the Euclid communities. There's been a lot of work so far. There's been quite a lot of papers, a lot of discussion about how science could be enhanced with Reuben and Euclid. This working group wanted to take that to the next step. So if we're going to do this, exactly what are going to be the data products that we would produce? So a charter was issued, and we were charged with coming up with an initial set of recommendations within 9 months. So just firstly, what is a Rubin-Euclid derived data product? The first thing we wanted to do was clearly define what is this derived data product. And the definition is that data are considered a Rubin-Euclid derived data product if the data product is derived from Reuben and Euclid proprietary data, but cannot be used to recreate any proprietary Reuben or Euclid data products. And this is quite important because Reuben and Euclid both have proprietary data, and there was quite a lot of fear that doing something like this might compromise the unique science of each of the two missions. So an example of protecting the unique science and not recreating proprietary data products from the Reuben side, this would be, say, protecting the time domain, which is quite unique to Reuben. So the individual measurements would be protected because the DDP would make, you would have a DDP that is based on all exposures, so depth driven, rather than exposing the individual measurements, the time domain of Reuben. Or for example, the depth of Reuben would be protected through a DDP that matches only sources that are visible above 3 sigma in the Euclid instruments. On the Euclid side, what Euclid seeks to protect is the high spatial resolution of its instruments, and this could be done through a DDP that exports only the photometry of isolated or deblended sources in Reuben. So this might be an example of a list-driven derived data product. And also the Euclid dropout science would be protected by limiting any derived data product to sources in common between Reuben and Euclid above 3 sigma, as seen in the Euclid instruments. Again, this would possibly be an example of a list-driven derived data product. So this was the basis, this is the definition, and this is the point that we started from. I'll just make here a note of some prior work that was done by the Tri-Agency Survey Coordination Task Force on synergies between Reuben, and Euclid, and just a couple of points here in the context of this derived data products working group. I'd say this point 4 here is probably one of the key ones to me, is that it underlines the importance of maximizing the overlap between the two surveys to maximize the scientific return, and in particular of synchronizing the observations between the deep drilling fields. And this is what I was talking about before with external synergies. What we're talking about here is how do we modify our survey strategies and observations in order to have synchronous observations which can then enhance the downstream science that is done. There are quite a few recommendations here. I won't go through them just in the interest of time, but this is here as interest for people to read up. This chart here is a very nice chart produced by Phil Marshall that shows the timescales for the data releases between Reuben and Euclid. You can see in the red you have the Euclid timescales, and in the green you have the Reuben timescales for observing, processing, proprietary access, and then full public access to the data. I won't go through every step in detail, but the key point I think to note from this is that there is significant overlap in the observing, both the observing, the process, and the access to the data. And I think this shows that there is a lot of potential here for producing derived data products and for synchronizing observations between these two surveys that can really produce an enhanced science. So the Rubin-Euclid derived data products, initially we were charged with organizing a workshop. And I think if we were in the before times, we would have organized probably something like a one-week workshop that would have been open to the community, and we would have had the working group get together, you know, early on to define what we wanted the report to look like, and then we would have had presentations and input from the community, and then we would have all worked together on writing the report afterwards. But given COVID, this really wasn't possible, and I was a little bit reluctant to organize a remote workshop for people you know, over a period of a week, especially when you had most Euclid people are based in Europe, most Reuben people are based in the Americas, and then we also do have people in Asia Pacific. And so I thought that would have been a bit onerous. So we came up with this idea of setting up an online forum which would allow people to contribute ideas asynchronously in their own time when things work for them. So we set up the Rubin-Euclid Derived Data Products Community Forum, which is very similar, and it's based on the ideas and concepts of the Reuben ls.st Community Forum. And you can see here that we had lots of interesting discussions about the various different science and derived data products that could be designed with Reuben and Euclid data. So this went on for a period of about 5 months, and just recently we had a closeout session where every working group, every science area presented its summaries, and the working group is now in the process of writing up the report. We designed the whole process around 5 questions. We first asked all the different people representing different science areas to think about what was their science case and what derived data product, what use cases were there for derived data products produced through joint pixel level processing, what information would they need, what about catalog level processing, what science would be enabled, and so forth. So what was the science driver for a particular derived data product? Then in response to that science driver, the idea was to design the derived data product. What exactly would the output data product look like, and what input data products from each of the 2 surveys would be needed to realize an output data product? So an example might be photometric redshifts produced by, an example of an output data product would be photometric redshifts, estimates of photometric redshift produced using information from both the Reuben and Euclid surveys, which would be better estimates than what you would get from either survey alone. We then also wanted to look at algorithms. Derived data products don't just produce themselves, and the algorithms that exist for individual survey processing might not be suitable for working with combined data. So do the algorithms exist, and do we need to do any sort of algorithmic investment to make these derived data products happen? And what do we need in terms of computing resources? Image processing can be quite intensive. So what was needed in terms of storage, what was needed in terms of access to image, what was needed in terms of CPU? And then the final question was around what timescales would the DDPs described be useful on. Some DDPs would be very useful in the early survey, and some might not be useful until you have at least 3, 4, or 5 years of data from Reuben or perhaps from Euclid. An example of a timescale of a science that would benefit from very early DDPs is a lot of the solar system science. So these were the 5 questions that we structured the discussion around. This is sort of the timeline that we've been working to. We started this around February. We had a couple of kickoff meetings, and the virtual discussion's been going on for about 5 or 6 months now. We had some summary meetings in June, and throughout August, we've now been writing the first draft of the report. This is ongoing, and the draft report will be circulated at some point for people to have a look at. I'm not going to share any of our preliminary findings or recommendations at this stage, or any of our specific suggestions or recommendations for derived data products, mainly because we're still writing it up and it hasn't received the blessing of the whole working group. But we're all working pretty hard on this, and we're pretty excited to get this report out. Okay, and that's it from me. Colin?
We have some general questions that I don't know if you want to leave the general questions for the end, or if there are questions specific to.
I think general questions maybe at the end, and we'll let the other 2 speakers go ahead. If there's anything very specific to what I've just spoken about.
There is one Euclid Rubin question from Johan. Maybe you'd like to ask that now.
Yeah, the topic of co-authorship is a difficult one. Co-authors who do not have data rights on all sides. Yeah, I think that, so we actually haven't really gotten to that stage of discussing how that would work. It is something that has to be discussed. This Derived Data Products Working Group wanted to focus on the science that would be enabled without letting the politics get in the way. So we will make a lot of recommendations and they might get rejected for exactly the reason of proprietary data. But we didn't want to initially start out by saying, well, we've got problems here with proprietary data and co-authorship, hence we're not going to even discuss what science could be done with this data. So we sort of removed that from the equation, started by taking a global view. The next stage of this process, once we've delivered our report and recommendations, will be to look at how we can move to the implementation stage and making it happen. And I think that's when the topic of how authorship and data rights of derived data products will be addressed. I hope that answers your question. Colin, what do you want to do next? Sindhu.
We have a hand from Il-Sangyun.
Can I speak?
Sure, go ahead.
Thanks. Just a quick question. So I'm just curious, there are quite a lot of discussions on the forum, and how are you going to summarize all of this and then make it into a report? Will that be a sort of high-level summary from the working group leaders, or the individual voice will also be on the report?
So we asked the working group leads for each science area to already gather that the inputs on the forum and to summarize them and to present them at our summary meeting that was held at the end of June. And they did a very nice job of summarizing all the key points and inputs. And the working group are now working to put that into a report. And it's a big job, and we're working on it. I personally am open to adding anyone as a co-author. Anyone who's contributed can be a part of this. My feeling is that the more support we have from the community, the more likely we are to be able to do this science and push these derived data products through.
Thank you.
Okay, maybe in the interest of time, we'll move on to Matt and try to deal with some of the other questions offline. So Matt, I'll just stop sharing. Go ahead.
Okay, hi everyone. Okay, are we good?
Yes.
Okay, great. Okay, so I'm very quickly gonna spin through some of the things you can do by combining the Reuben data with the radio observations. So in particular in this talk, I'm just going to talk about things in the Southern Hemisphere which are doing huge surveys, which is going to maximize the overlap with Reuben. So there's lots of other things that could be talked about, which could be brought up in the discussion. So why would you want to bother with the radio? So some of the science that we can get from the radio is things like looking at extended emission, so to do with radio galaxies and diffuse radio emission and things like merging clusters. You can get information on spectral indices. So if you're interested in AGNs and feedback for galaxies, this can tell you when AGN feedback was happening. You can also get dust unbiased star formation rates. So if you're in the radio, obviously you don't have the problem with the dust that you do if you're looking at optical and UV. And then, of course, one of the big focuses of the new generation of radio telescopes is looking at neutral hydrogen, so the famous 21 centimeter line. This, of course, is going to get you spectroscopic redshifts for loads of galaxies in spectral cubes, which you can then, use potentially to improve photo Zs done by ls.st in the future, for example. And of course, the H1 is also going to tell you about where the field for star formation lives, and by measuring the H1 mass as it changes with redshift, you get an idea about what's going on with star formation in galaxies. There's obviously a lot of overlap with work being done by DESC. So one of the things you can do with the neutral hydrogen is this new technique called intensity mapping. So mapping the large scale neutral hydrogen distribution. So by combining that tracer with the tracer from the galaxies, you can get tighter cosmological constraints, for example. And the last bullet point there about polarization is about measuring magnetic field strengths, which you can do with radio data. So obviously a big focus for ls.st is transients in the time domain. I have to say I'm not on home territory talking about this. So here I've just got a collection of things which people are looking at in terms of radio transients, particularly the last three, gamma ray bursts, supernovae, and fast radio bursts, things that go bang. Fast radio bursts in particular, we've only known about since about 2007, and it's still a bit of a mystery what those are. Obviously, Reuben data combined with the radio is going to hopefully tell you what's going on with those guys. Okay, yeah, so Meerkat is probably the best radio telescope in the world right now in the Southern Hemisphere. I'm obviously a bit biased because I'm actually based in South Africa. So this is an array of 64 13.5 meter dishes with wideband receivers at the frequencies listed on the left. On the right, I've just got a few example images from Meerkat. So this is the deep 2 field, so-called Meerkat deep 2 field. Most of the little tiny dots you can see in here are going to be star-forming galaxies at fairly high redshifts, potentially. There's also going to be AGNs in here, of course, and you can see some. If you can see my mouse pointer, there's one of your classic double-lobed radio galaxies in the bottom corner there. You can also look at extended emission. So this is a nice X-shaped radio galaxy observed with Meerkat. So the nice thing about the new generation of radio telescopes is they've got these dense cores, so you can get this access to the large scales, which you don't necessarily see with things like VLA, for example. So this is something on a scale of about 22 arc minutes here, and you're obviously seeing a lot of the structures in these AGN jets here. And then if you're interested in the galaxy, this is one of the earliest Meerkat images that was released. This is of the galactic center. So this is the center of the Milky Way with lots of weird and wonderful things happening in it. So Meerkat's been observing since 2019. About 2/3 of the time is already taken up with this bunch of surveys, which is mentioned here. But what might be of interest to this audience is that you can apply for Meerkat time. It's not as anyone in the world can apply since the last September 2020 call for about 1/3 of the time on the instrument. And yeah, the archive is also going to be a useful resource, I think, for Reuben. So there's a lot of scope for doing serendipitous science with the thousands of square degrees that will be covered by Meerkat because it's got this huge field of view. There is also an Australian square kilometre array pathfinder. So this is called Ascap, which is a similar kind of instrument to Meerkat. So this has got a bit worse resolution. So it's something like 10 to the 15 arc seconds. And the things which might be of interest is that this is really a rapid survey instrument. So it's covered areas of like 30,000 square degrees, these two surveys which are highlighted at the top here. And there's a bunch of other surveys which are going on looking at things like transients and so on. Of course, what these two instruments are doing is feeding into what's going to be the square kilometre array. As of the start of this year, this is now, they've formed an organisation to go ahead with this. It's going to consist of 2 telescopes, one in South Africa, which is SKA1 Mid, which is going to incorporate Meerkat somewhere around 2027. So Meerkat will be available for a few years before then, before it gets absorbed. And then there's SKA1 Low, which is going to be in Australia, and this is more focusing on the epoch of reionization, so very early universe stuff. So probably SKA1 Mid is probably of more interest for Synergies with ls.st, I would guess. In terms of how this is going to work, I don't think this is defined at this stage, but the general plan in the operations document seems to be that there's going to be key science projects, so big surveys which can be defined. You'll also be able to apply for time on this, so PI projects will be there, and there'll also be open time, so it's not just limited to necessarily people in SK partner countries. Just an example of the combination of SKA with ls.st, you can find this in the SKA 2018 Cosmology Red Book. So that talks about the suggested surveys of, say, 5,000 square degree H1 survey, so getting the line emission from the galaxies at fairly low redshift, or a 20,000 square degree survey doing this H1 intensity mapping technique. And so if you put that together with the Reuben ls.st galaxy catalog, so you combine these two different traces, you can get constraints on, for example, this is FNL, this is the primordial non-Gaussianity parameter. So this constraint here the error bar on this is actually 5 times more precise than what's been done with the Planck satellite. And of course, the other thing you get with the new radio surveys is this commensal observing mode. So while the instruments are surveying whatever they're looking at, they can also be running in the background fast imaging pipelines to search for transients. So you can potentially put that together with what's going on with ls.st. And yeah, so this is all going to be happening a few years after ls.st starts. I just wanted to mention this other experiment. So this is also taking shape in South Africa. So you may have heard of CHIME. This is this H1 mapping experiment in Canada, which is also finding these fast radio bursts. There's a similar southern experiment, but using dishes, which is being put together at the moment. And again, this will cover a huge area with overlap with ls.st, and as well as doing the H1 cosmology, we'll find lots of these fast radio bursts. And so I've got a little result here from CHIME at the bottom. So the number of these fast radio bursts per sky per day is something like 800. So there's no shortage of them. But at the moment, I don't think it's particularly well understood exactly what these things are, and there could be a whole variety of things. So just to finish in the last couple of minutes, I wanted to stretch the radio into the millimeter wavelengths, and this is really talking about the large ground-based cosmic microwave background experiments. So the current ones are Atacama Cosmology Telescope and South Pole Telescope, but shortly we'll have a project called Simon's Observatory, and then in the future there'll also be CMBS4. So you can get an idea of the kinds of data, what you get out of these surveys by looking at the recent ACT data release, which is on Lambda. So I've got links in here. So there you're getting multi-frequency maps of a large chunk of the southern sky. So the recent ACT releases is covering 18,000 square degrees at multiple frequencies. And there's a lot of data products which can be combined with the Rubin ones, in particular if we're talking about with DESC to do cosmology. So things like the CMB lensing, potential maps telling you about the large scale matter distribution. You can look at the thermal Sunyaev-Zeldovich effect, which is telling you about the gas pressure. You can learn about feedback and things like that. We can produce cluster catalogs. We saw some examples of SA catalogs combined with DES in the plenary this morning. And then we've also got the point source populations, so things like dusty galaxies and AGN. Something we'll also be able to do in the future, which is looking at transients in the millimeter, which seems to be new territory. Here I've just got a slide showing where Simon's Observatory is going to be. So this is actually the ACT site in Chile. So this is actually under construction at the moment. And yeah, in terms of the interest to ls.st, then probably the thing which is most interesting is the Large Aperture Telescope, which has got sort of arc-minute kind of resolution and is starting observations in about 2024. So the same kind of time that ls.st is going to, and Reuben is going to start operations. So yeah, so the new opportunities here with the millimeter wave is looking at things like varying sources, which has not been done before at millimeter wavelengths. So you can look at AGNs, for example. On the right here, I've got an example of the first ACT transient, which was reported, which was probably associated with a flaring blazar. So this is all very early days, but there's been a couple of other recent papers on this. So from ACT, I've got this detection of flaring stars in this paper by Sigurd Ness. This was a result of a Planet 9 search, so this was not really a search for transients as such. And then from SPT3G, there was also this result where they found more flaring stars, and this was actually a proper transient search, as it were. And this plot on the right is just showing that these things are all over the place on the HR diagram from Gaia. So I think I'm just about over time there, so I think I'm going to stop and just leave up my little summary slide, and yeah. That's it.
Great, thank you, Matt. I see lots of interesting questions coming up in the Slack, but I think we'll leave those until the question and answer session to go through. Are there any just very quickly specific questions for Matt on his talk? Anyone wants to raise a hand and ask? I'm not seeing any. Okay, let's move on to Matthew Graham. Okay. You could unshare, thank you.
Right. Okay.
Right, looks good.
Good, great. Okay, so thanks for Leanne and Rachel for asking me to talk this. I feel like the poor cousin or the poor country cousin because we're not a $100 million plus facility. We're a 70-year-old ground-based telescope, 1.5 meter, though we are running. So we are producing data and have been doing through COVID. So the question is, what can ls.st and ZTF do together? Or what can you do with 1.1 LSSTs? And the reason I say that is because ZTF is really about a 10% LSST in many ways. Certainly in terms of our alert production, because ZTF is a dedicated time domain astronomy facility. It's the only thing we care about. We're not particularly interested in cosmology. We're not particularly interested in dark energy. What we are interested in is transient and variable phenomena in the sky, and that's the sort of the main focus of ZTF. So we've been running ZTF since March of 2018. As of September last year, we had actually surveyed the same area of sky that LSST will do in its 10-year. That's about 22.5 million square degrees in the Northern Hemisphere, and obviously not to the same depth. But this is one of the advantages of ZTF. Because it's a Schmidt telescope, we have a very large field of view, 47 square degrees. And our nominal 5 sigma detection limit for a 30-second exposure is 20.5. We have 3 filters, though most of you probably only ever see data from 2 filters with the GNR, but we do have an I filter, which is used by the partnership. And that data is slowly becoming available through our data releases. But in terms of coverage, we look at everything from Palomar, north of a deck of -30, now on a 2-night cadence for the public survey, which is about 50% of the time in GNR. And so this means that we have, there are areas of sky where we have observed more than 1,500 times, 1,500 times over the last 3 years. Now, there is a big question, of course, of with LSST starting on the 1st of April 2024, will ZTF even be operating then? Because our nominal end of ZTF2 is 30th of September 2023. So there was potentially not even 1 day's overlap. But what seems likely to be happening is that we will be doing a year 4 of ZTF2, and then there's whatever ZTF3 will look like. So we can anticipate that there will be, at least early continuity for ZTF into the LSST survey, science survey area. So one of the things I think you want to be thinking about, but as a 1.5 meter versus a 6.5 meter, even if it's north versus south, is that there are areas of overlap, particularly in the equator. If you go deck -30 to deck +30, there's a good overlap region there. And we know from ZTF that we can do coads to a great depth. So our coads can go to 23rd magnitude, and we have had programs in the partnership time where people have looked at faint transients by coadding data together so that they get a data point every 3 or 4 days from higher cadence observations of particular regions. And so it's not a 2-night cadence single observation. You're looking at a cadence point, maybe, as I say, every 4 to 5 days, but down to 22, 23. And so that then increases the region of the volume of overlap and the region of overlap in magnitude space between the 2 telescopes potentially. So I think that's one thing to consider with ZTF. We may be not so faint in a single, but co-adding, we know we can go fainter. The other thing I would say is about alert structure. I think we're very proud in ZTF that we've driven a lot of the alert infrastructure production for LSST and getting things going. We're about to move to force photometry in our alert packets, which I think will make us closer to what LSST will be doing. And so there will be more training ground there. But again, there's stuff that we could be doing as a synergy in this arena, which may help with some of the things that are thought of down the line. How do we coordinate alert streams between all these different surveys which are producing alerts? And maybe that's something we should be thinking about now as we transition into the pre-ops phase. From a scientific basis, so therefore, what could we do? Let's say we have a ZTF 2.1 and something further. So I think the big win from ZTF is our sky coverage. as I say, we have 47 square degrees versus 9.6 square degrees. So we can cover much larger areas far more quickly. Eric Feigelson had a statement at the start of this week that ls.st time series features will be uncertain. 3 sigma tests are not possible until at least 2027 on the basis of the current ls.st cadence. Now, what happens if you have ZTF covering some region of sky to a reasonable depth through coads at a much higher cadence? What does that open up? Potentially filling in gaps where ls.st then comes along and provides secure anchoring for very accurate photometric calibration and things like that. And ZTF is filling in the gaps at a noisier level, but still at a higher cadence, which will help you get these basic statistics. So one way we could do this is hammering the equator. We have a nightly high cadence program with the ZTF where we would have a very high dedicated program just to hammer whatever is observable from Palomar 4-6 times a night in GNR, and you do that over 4 or 5 nights. That gives you 16 data points or 16 images per filter. You do co-add that's a current ZTF reference image then, and that'll go down to 23, 23.5. So could that be useful for them? Another question you can ask is actually, let's flip this around. Let's not ask what ZTF can do for ls.st, but what can ls.st do for ZTF? We survey these large areas of sky. We find transients. Some of them are quite faint for our detection limits, but it would be great. So let's say we have a supernova. Can we go back and see what the ls.st observations for the previous 2-3 months of that region of sky were, to see whether there may have been fainter, pre-supernova burps, things like that, looking for the precursor death omens of exploding stars or transients, or at some point these transients decay below our detection limit, but they'll still be followable by ls.st. So can we do things there? Galactic plane again is an area where it's a little unclear what's going to be done there with ls.st. We do the galactic plane in ZTF, and we have dedicated deep drilling plans for ZTF with partnership time, where we will sit on fields in the galactic plane and hammer them for 2-3 hours at a time. So that gives you very high precision or very high cadence time series. You could imagine we could continue doing that, and again, ls.st coming in and providing anchoring points and filling in gaps where necessary. There's this whole area of EMGW follow-up. Obviously, we do this as a matter of course with LIGO in 03. We will be doing so in 04 and 05. Large area coverage down to some depth. ls.st again provides the fainter end of that. And then I would say finally, just again, this idea of evolving alert infrastructures. Could ZTF have a continuing role as an ls.st test bed for new things that want to be done with alert packets, different forms of alert packets? The ZTF alert packets at the moment are up to 70K in size, which is very close to the 80K that ls.st are talking about. But what about lightweight packets? Other things that could be done with that as well, that we could be feeding into the existing brokers, and all of the brokers that have been announced are ZTF customers, that we could be developing that. And are there not necessary science synergies, but science infrastructure synergies that ls.st and ZTF could be providing together? So this is, from my perspective, this is food for thought. Obviously, anything we can do to help ls.st may help in continuing funding for ZTF as well as we go forward. So yeah, I think it's a very interesting area to consider what can be done with a small ground-based 70-year-old telescope, as opposed to a multi-$100 million space-based thing or whatever. And I'll leave it there. Thank you.
Great, thank you, Matthew. All right. Okay, so we have about 5 minutes left now until the end of the session. Colin, I will let you be a master of the questions.
Okay, Tom Wilson had a good question. If you'd like to repeat that for the Zoom audience.
Yeah, sure. Yeah, my question was actually to flip Leanne's first slide, where you explicitly stated that non-pixel level mapping analysis was not an external synergy. So I just wanted to ask where the discussion of those kinds of things was taking place. this presumably involves you take your ls.st and you cross-match it to something else, your infrared data or whatever. Where are these discussions happening in the community or within Reuben, if not here?
It sounds like Leanne walked away to tame the dog for a moment. So.
Yeah, sorry, dog problem. Yeah, that's a good question. So I think in terms of things like, I'm just reading your question here, cross-match. This is something that's, ls.st isn't going to provide a cross-match service, and we're not going to provide cross-match with other catalogs. This is something we consider to be in the community domain. And there have been a lot of efforts ongoing around providing cross-match between, say, Gaia, ls.st, and many other surveys. This has done a lot. The community brokers have been working a lot on this. I know that there was even talk of, at one point, of them getting together to try to produce some sort of common cross-match service that they could all use. So that's one place you could look at, or you could just ask on community. I mean, who's looking at cross-match? What sort of cross-match services exist? This is clearly something that I think as we move forwards is going to become more and more important, some sort of automated cross-match service. It is outside of the scope, though, of Reuben Observatory and the ls.st to provide that, and it's not really what we're thinking about in terms of external synergies. Does that answer your question?
Yeah, I think so. Community.ls.st is pretty much the secret buzzword.
Yeah, I mean, do go there and ask the question and start a discussion. I know a lot of people have done work on this, but the community brokers themselves, they're very focused on once you get the data products from ls.st, the alerts about combining those products with other surveys to optimize follow-up, and they'd also be a great resource. ls.st has recently selected 7 full stream community brokers, as well as 2 downstream community brokers. So we have a total of 9 community brokers that will be focused on these topics, and I think they'd be a great resource. Matthew is leading one of them.
Okay, there's a question from Yogesh. If you'd like to repeat that again for the audience.
So I just realized that the filter set of the Roman-wide surveys is very nicely complementary to what Reuben will use, near infrared versus optical. And this could be very critical to get accurate photometric redshifts. So the question was, what effort is happening in the Rubin-Roman synergy to look at this in a systematic manner?
Yeah, that is a great question. I agree with Colin. You're putting me in a position where I have to preface what I say with spoiler alert. And what I'll say is that this is one of the synergies that came through the strongest in the Derived Data Products Working Group. Certainly improved photometric redshifts and the improvement that we can get from bringing in the Roman filter set, the Rubin, at least the Euclid stuff, and it would be Roman as well. They're very obvious, they're very strong. It's almost like it's the lowest hanging fruit, and if we do anything, we should do this. So spoiler alert, we're going to be strongly recommending to do that out of the Rubin-Euclid Derived Data Products Working Group. I presume that would also be the same with Roman. I might let Julie answer and say something to this as well.
Yeah, I mean, I don't have anything immediately sensible. I agree with you that it is one of the first things that immediately come to mind. The group within Roman that will have looked at this are the High Latitude Science and Survey Science Investigation Team, and someone from that team would be more qualified than me to discuss what has been done. I could certainly comment, though, that this is exactly the kind of thing that I think would be a very valuable thing to propose for in our upcoming proposal call.
Yeah.
Yes, thank you very much.
Maybe one more question from Dan Tranu.
Sure. So I've paid some attention to the joint derived products working group, but I'm still very confused about yeah, the scope for joint pixel level processing, especially since at the beginning you mentioned an example about preserving the advantages of both and how that could mean analyzing isolated galaxies only, and that would be based on an isolation criteria in Rubin or Roman or Euclid or both, or how exactly that would work. I understand there are political issues with data sharing, but I don't know to what extent the working group is supposed to skirt around those or sort of promote as much data sharing as possible.
When you say is joint analysis of co-added images from both surveys possible or not, do you mean possible in terms of politically, is it going to be possible because of the proprietary data issue? You're not talking technically here.
I think it's clear it's technically possible. Politically, yes. Also considering, I mean, there would be a substantial number of people with data access to both right away who could presumably do this on their own without permission.
So I don't know if Jean-Charles is still on. I'll also let him maybe weigh in on this, but Jean-Charles and I at the beginning of this Derived Data Products Working Group made a decision that we would try to remove all forms of politics and data rights from the discussion, that we could focus on what science could be done if we could access all the data without any hindrance. And then we would go and talk to the respective surveys, projects, agencies, etc., and say, well, here's what we could do. Now, what are you going to let us do? So I don't have a solid answer for you yet about whether that can or can't be done. That's going to depend upon what, how much science improvement we think we could get from a processing, and what sort of, and then how the various agencies would react to that, in terms of, you know, how that affects their proprietary science and their unique science and their publications. I think that's addressing those sorts of questions is going to be the next stage in this process. Once this working group's report comes out that says, well, here's the science we can do and here's what we recommend in terms of the types of derived data products that would enhance science, it's going to be, well, now what are we going to do on what timescale? And I think you also raise a point about public data access as well. And certainly once the data becomes public, it's public. So do what you want with it. Does that answer your question?
To some extent, but feel free to move on because I see other raised hands.
Okay.
Slack queue is empty, so I'll let Leanne handle the rest of the raised hands or the time constraints.
Okay, we are over time actually, so if you want to go, you can go, but I'm happy to stay here and continue to take questions. Julie, let's go. Julie's raised her hand.
Yeah, I actually wanted to comment on the last question a little bit. The discussion of proprietary data is very different for Roman than for Euclid. So it strikes me that a lot is going to depend on the relative time of data release between Roman and Euclid, which I think is, you know, somewhat uncertain because we're all over the place with COVID-related impacts. I mean, another way of phrasing this is that if there are things that you could do with either Roman or Euclid, and the Roman data are available and publicly available, that might make it more politically advantageous for Euclid to be more relaxed about their data policy.
That's a good point, thanks. Tony?
Yeah, Julie just made a very good point. You know, this conversation with Euclid has been going on actually for several years, a number of years. And I think that we all recognize that joint pixel processing is the right thing to do, particularly with a high resolution thing like Euclid. And it's a lot of work and it's going to take time to get it right. And so there's been some discussion of forming a small group, a joint group between ls.st and Euclid in the community to actually do this. And by the time it's finished in some part of the sky, to export that technology to the surveys in the after the proprietary time is over. But it's going to take a lot of work, and you don't want to wait until it's open data to start.
That's a good point. Okay, do we have any final questions or comments? We are now about 5 minutes over time, so I think I should let people know. Okay, well, I'd like to thank all the speakers today and everyone for coming to the session. You know, we had 70 or 80 people join. I think it was a really good session. And enjoy the rest of the project and community workshop. Bye.